first is going to be by Phil Thomas. So he's an assistant professor at the University of Massachusetts in Amherst, or I guess you've been for a few years. You were previously a postdoc with Emma. And he's going to be telling us all about safe and fair machine learning.
Thank you. So the title is Safe and Fair Machine Learning, but within machine learning is the subfield of reinforcement learning. So everything that I'll talk about will apply to reinforcement learning, even though you'll hear me every now and then talk about some supervised learning stuff. And I'd like to just start off by thanking my co-authors on this. This work could not have happened without all of them. All of these were co-authors on some of the papers that I'm going to be talking about. Okay, so I'm going to start with just a couple of claims, starting with ones that I think aren't too controversial. So the first one is that machine learning algorithms should avoid undesirable behaviors. And what do I mean by undesirable behaviors for a machine learning algorithm? Well, one that comes to mind is fairness. So we want our machine learning algorithms to behave in ways that are fair. We don't like when these kinds of articles come out because it implies that something unfair happened, like the New York Times one on artificial intelligence's white guy problem, or one that I'll talk a little bit more about. I suspect most people have heard this at this point, but it was an article by ProPublica looking at some software that was used to predict whether someone would commit a crime in the future. So the input is a description of the person. The output is they will commit a crime in the future, they will not commit a crime in the future. And this was used in 11 states during criminal sentencing. So when the judge is deciding what someone's sentence should be, they were given the output of this machine learning algorithm that was predicting whether someone would commit a crime. And ProPublica did a study on this piece of software and found that it was twice as likely, if you just consider the people who will not commit a violent crime in the future, it's twice as likely to make an error and say that they would if they were black than if they were white. And so this is an example of what we might consider undesirable behavior of our machine learning system. In the reinforcement learning setting, a problem that I like to talk about is type 1 diabetes treatment. So first, a quick brief intro to type 1 diabetes. What happens is this plot is a plot of someone's blood sugar throughout a day, and each blue curve is a different run, a different simulated day. And so what happens is you eat breakfast, your blood sugar goes up, your body releases insulin, which promotes the absorption of this sugar in your blood glucose, into other cells in your body, and your blood sugar comes back down. And then you eat lunch, and it goes back up, and then your body releases insulin, and it comes back down, and this process repeats. The 3 humps are roughly breakfast, lunch, and dinner. Someone with type 1 diabetes, their body doesn't release enough insulin. And so there's not enough of this promotion of the absorption of blood sugar from the blood into cells, meaning the blood glucose does not come down. So it stays up too high above some threshold. So that threshold is where we call, if you're above this, it's called hyperglycemia. Hyper for too much, glycemia for sugar. So this is called hyperglycemia. Someone with type 1 diabetes will often suffer from hyperglycemia. Extended hyperglycemia can cause ketoacidosis, and I think it's the leading cause of non-traumatic amputations. So it's a severe problem. And the treatment for this is that someone with type 1 diabetes can inject insulin into their blood manually or with an insulin pump. So this insulin pump would take a measurement of the person's current blood sugar levels and then decide how much insulin should I inject in order to properly regulate their blood glucose levels. So if it injects too much, it could drive blood sugar to be too low. And if blood sugar is too low, that's a condition called hypoglycemia. It differs by a letter, but big difference between hyperglycemia and hypoglycemia. Hypoglycemia is much more severe generally than hyperglycemia. So severe instances of hypoglycemia can cause you to lose consciousness, which could be devastating if you're driving, and can effectively lead to death and severe consequences. I think a severe instance of hypoglycemia triples the 5-year mortality rate. So we really want to avoid hypoglycemia while trying to avoid hyperglycemia. How is this a reinforcement learning problem? Well, the state is a description of the person. It's all of the information that's being fed into this insulin pump. The action is how much insulin we inject. And some reward would be some penalty for deviation from those optimal levels, with perhaps a bigger penalty for low blood sugar. But the original claim that I was starting with for this slide was machine learning algorithms should avoid undesirable behavior. What would undesirable behavior be here? It would be increasing the prevalence of hypoglycemia if the algorithm deployed a policy that caused more hypoglycemia, right? Okay, what's another example? Another example is targeting ads. So here I went to Microsoft's page, and I'm actually not sure how they do this, but often these ads are targeted. This is not a random or fixed ad for many companies. What's happening is there's a description of the person visiting the web page that comes into the system, and there's a set of ads that it can choose to show, and then the system will decide which ad should I show to this person in order to maximize the probability that they click on it. So the state here is a description of the person. The action is the ad or type of ad that I show them. and the reward is +1 if they click and 0 if they don't click. So in the reinforcement learning setting, maximizing the expected reward means maximizing the amount of clicks that we get on our ads. What is undesirable behavior here? It would be what happens if I deploy a policy for serving up these ads that's actually worse, and it decreases the click rate. I mean, it's very different from the previous undesirable behavior where it causes harm, but here it could cause financial loss or cause a product team to not like a research team or something of that sort. Okay, so next claim. The next claim I'd like to make is that undesirable behavior of machine learning algorithms is causing harm. So you might think undesirable behavior of machine learning algorithms, this is something to talk about like Skynet and crazy distant future stuff. It's not. It's something that is currently already affecting us, and I'd like to argue perhaps more than you might think it is. So first, in the supervised learning case, I think this is a clear argument that it's already causing harm. What about in the reinforcement learning case? So I'd like to start off the argument that undesirable behavior is negatively impacting us in reinforcement learning by just talking about some proposed applications. We had diabetes treatment in the top left. The one next to it with the frog, this is a picture from some work that Emma Brunskill did. She did a lot of great work on intelligent tutoring systems, where there the state is a description of what a student knows, and the action could be something like how difficult of a problem to give them next, or what topic to teach them next. And the reward is at the end, you give the student a quiz, and you judge their performance, their knowledge at the end based on the score from that quiz. So the use of reinforcement learning algorithms to improve these intelligent tutoring systems is a wonderful potential application. Ads we already talked about. The one on the bottom left is epilepsy treatment. I think some of the folks at McGill did a lot of work towards trying to apply RL to epilepsy treatment. And the bottom right one is sepsis treatment. There have been a few papers on that recently, but mainly I want to talk about just medical applications of RL. There have been many proposed applications of reinforcement learning to medical applications. But something that I notice when I look at these is that most of these are proposed applications. They're not deployed applications that are impacting our lives. So if you think about supervised learning, it's everywhere. It's unavoidable, right? I mean, supervised learning is on your phone, in the swipe functionality, in your spam filter. If you put a letter in the mailbox, it's optical character recognition to decide where it goes. You cannot avoid supervised learning. That's much less true of reinforcement learning. Right? There are some applications, but far fewer. Most of these remain proposed applications. And why is that? Because we have a lot of really cool successes of reinforcement learning that have been building its popularity. So these successes are typically on video game style applications, which is useful, as we heard about earlier today. I'm not meaning to say that these are not useful applications that are beneficial. I'm just pointing out that there's a divide between these two, and why is it that RL is having such great successes over here, but it's not doing so well on those other real-world applications? My belief about this is that it's because of undesirable behavior. RL algorithms, when you tell them maximize the expected return, they don't. The first time you apply RL to a problem, it typically completely diverges. And you say, well, my step size was too big. And then you try a smaller step size. And then you tweak your architecture, and you tweak the eligibility trace decay rate, and you play with your reinforcement learning system until it's working well for that application. And that's great. We can optimize the step sizes for the Atari playing agents with a grid search and lose millions of games of Atari on one of Google's compute servers. That is totally okay. But that's not okay for one of these real-world applications. We can't tell a patient, sorry, we botched your treatment, hopefully we'll get the hyperparameters right the next time. So this is my argument. It's that we can't have these undesirable outcomes when we apply a reinforcement learning algorithm, even the first time, to a real application. If we deploy a policy, and it's a change from our current policy, it needs to be at least as good or better. We can't have this deploying of policies that are much worse due to something being wrong with how we tuned our system. And so why is this causing harm? I argue that this causes harm because of a lost opportunity cost. These are applications of RL that I think are very nearly within reach, or perhaps some of them are within reach. And they're not happening because of these fears about undesirable behaviors of reinforcement learning systems if you were to apply them. Okay, so can we create algorithms that allow their users to more easily control their behavior, that allow the user of the algorithm to say, this is what I want you to do or don't want you to do, and the algorithm somehow then does that? So what do we want out of an algorithm? We want it to be easy for users to define undesirable behavior. So in the classification setting, there's a paper, 21 Definitions of Fairness, and there are more. This stems from the fact that what people view as undesirable behavior for their application can differ from what someone else views as undesirable behavior. And so if we want our algorithm to actually be used, we we need to give the user the ability to say, for my application, this is the definition of undesirable behavior that I think corresponds to what I want. And if our algorithm doesn't guarantee that that kind of undesirable behavior won't happen, the person's not going to use it. And we shouldn't expect the person to say, for my new application, this is what undesirable behavior is, or this is a new definition of unfairness or fairness that I want to have enforced, and then have to go to the research community and say, now develop a new algorithm for that definition. That's not how it should work. It should work where they say, this is my definition of undesirable behavior, and the algorithm takes care of the rest. Another example of this is in diabetes treatment. One of the standards in the literature is mean time hypoglycemic. So you want to decrease the mean amount of time that's spent hypoglycemic, but another reasonable choice would be to weight that by the severity of the hypoglycemia. So you don't just take the mean time, you weight it by the severity. And these are two different definitions that someone might choose to use. Okay, so once a user has told us what they think undesirable behavior is for their application, our goal is to guarantee that the algorithm won't produce that behavior. It's not enough for us to give you an interface to say, this is my objective function, maximize it. It doesn't matter, though, if you actually do. That's not enough. If the user says, this is my objective and I want you to maximize this, we need to give some guarantee that we're going to do that. Okay, so in picture form, what do we want? We want to create an algorithm A, which takes as input a data set D and some expression from the user. Maybe they just say, they speak to their laptop and say, learn to predict loan repayment and don't discriminate. So here the input is a description of a person and the output is whether or not they repay the loan. And don't discriminate. And the output of this should be a solution theta that is, in this case, a classifier. So x1, x2 are features of the input. And then the classifier corresponds to the green versus red region saying, I predict that person will repay or not repay. Okay, or we might want the person to be able to say, learn to predict job aptitude based on resumes, so that we can quickly filter resumes but don't discriminate, and it should come up with a classifier for that. The person should be able to do this in the regression setting. They should be able to say, learn to predict how far a landslide will travel, but don't underestimate, because this was something I actually saw geologists doing, where they were using linear regression to use features of a slope to try to predict how far the landslide would go in order to determine how far away a house should be from a slope. And so in that case, you really don't want to underestimate how far this landslide will go. And in that case, it should output a solution which is a regression model. Okay, what about in reinforcement learning? In reinforcement learning, we might want something like learn how much insulin to inject, but don't increase the prevalence of hypoglycemia. And we want our algorithm to take this and output a policy, which in this case, this is kind of a standard-ish form for some of the insulin pumps. They sometimes have a couple more parameters, but something like injection size is the current blood glucose minus the target blood glucose, divided by one parameter we can change, plus the meal size in grams of carbohydrates, divided by a second parameter of our policy. So this looks a lot like a PD controller, but note, this isn't a deep network. This is roughly 2 or 3 parameters to our policy. Okay. So let's think a little bit more about one of these examples. It won't be RL, but the same issue will arise in RL. What if someone says, predict the average human height, but do not overestimate? And we get data from these 7 people, and we compute the average, and it's 1.7. We're not done, because the person said, don't overestimate. What number should we output to make sure that we don't overestimate? What if we had 1,000 samples? What if we had data from 1,000 different people, and the person says, don't overestimate? What can we do? The only thing you can output is 0. Yeah, someone said it. Exactly. We could have been unlucky. The people that we sampled and measured the heights of could have been the 1,000 tallest people in the world, right? So we don't know if we're going to overestimate or not, and we can't know that due to the random nature of data. So instead of requiring this to be deterministic, if we view this as kind of our overall model, achieve some main goal, but don't produce undesirable behavior, we need to give the ability for the agent to reason probabilistically, to say data is random, I can't guarantee anything with certainty, but I can do it with high probability. So the user now is going to specify this probability delta, and the algorithm should ensure that the probability it produces a solution theta that doesn't satisfy this constraint on undesirable behavior should be at most delta. So let's look at an example. Learn how to predict loan repayment, but don't discriminate. And I want a probability of 0.01 for delta. That means the probability that this algorithm can output a solution that does discriminate needs to be less than 0.01, where the randomness here is coming from the data set that we're training on. Okay, but what if we try to do this using data from just 4 people? So if I asked you, build a classifier and give me guarantees about discrimination from 4 people's data, this is a hopeless task. 4 people's data is not enough to make any conclusions about the world, right? Other than the existence of 4 people. So what can we do? We can't solve this. There's another similar problem, which is going to have the same end solution. And for that, consider the diabetes treatment one. But if the person said, learn how much insulin to inject, but don't ever allow blood glucose to deviate by more than 1.2 mg per dl is like a pixel in that previous plot. This is not possible. Your blood glucose is going to deviate by more than that. So the person could, in this case, have asked for something that is impossible. And in the previous slide, the person could have asked for something that we cannot do with the amount of data that we have. And in both of these cases, the fix is the same, and that's to change our setup. In the bottom right now, we allow the algorithm to say no solution found. This is its way of indicating, I can't do this. That could be because I don't have enough data to do it, or because you asked me to do something that's impossible, right? Okay, so let's revisit what it is we wanted out of these machine learning algorithms. The algorithm should provide an interface for the user to define what they consider to be undesirable behavior. They should be able to specify that probability delta, and then our algorithm should guarantee that the probability it produces that undesirable behavior is at most delta. Okay, so let's just formalize this a little bit. Let's define D to be all of the training data, which is our source of randomness. Let's let theta be the set of all possible solutions our algorithm can return. It's the space of policy parameters in RL. Let's let F be the primary objective. So F takes theta, a solution, as input, and outputs some measure of how good it is. In RL, this is J. It's the expected return or expected discounted return. Let's let A be a machine learning algorithm. So what is an algorithm? It takes a data set as input, and its output is a solution. So A of D is the solution output by the algorithm when it's run on data D. Okay? Next, let's define a function G. G is going to be our measure of undesirable behavior. So it takes as input a solution and outputs a real number, which is a measurement of how much undesirable behavior does this solution produce. If this number is less than 0, we say that theta does not produce undesirable behavior. So if g of theta is less than 0, it does not produce undesirable behavior. If it's greater than 0, it does produce undesirable behavior. You might be saying, but why don't we just make this a Boolean function? G of theta is either 0 or 1. That would be equivalent. By doing it with this real valued form, it'll be easier to create some of our algorithms, as you'll see soon. Okay, with me so far? Okay. Oh, there's one other thing, which is we need the algorithm to be able to say no solution found. So NSF stands for no solution found. It is in our set of possible solutions, and it is safe to return. So the algorithm can return no solution found, and it's not incurring a failure because of that. Okay, so revisiting what we want with this new notation, we want the user to be able to specify undesired behavior, which means the user specifies G. They specify the measure of undesirable behavior, and we then want to optimize that primary objective F, subject to this constraint. Let's walk through it. The probability of, and then it's going to be something is greater than 1 minus delta. Deltas are probability of failure, so this is with high probability something should happen. What is that something? A of D is the solution returned by our algorithm. G of A of D is then that measure of how undesirable the behavior is of that solution. And so G of A of D being less than 0 means that the solution returned by our algorithm does not produce undesirable behavior. So with high probability, the solution returned by our algorithm should not produce undesirable behavior, is what this is saying. So written out, probability the algorithm returns a solution, exactly what I said. Ooh, I got it. The probability that the algorithm returns a solution that produces undesirable behavior is at most delta is the flip of this. Okay, so we need a name for this. And originally what we were going to call it is, we call this an algorithm that satisfies the safe. And we quickly moved away from that because safe has become very heavily used in machine learning to mean a variety of different things. Even in reinforcement learning, safe reinforcement learning can mean very different things to very different people. We had a paper on safe RL at one point where the reviewer said, this has nothing to do with safety. And we obviously disagreed. And so safety is an overused word at this point, and it's not clear what it means. So we wanted something more precise, so there's no debate about what does this mean. It simply means that equation at the top. And so we decided not safe, and we ran through some others like delta safe. And in the end, we decided to call it Seldonian, which, if anyone is a fan of the Foundation series, yes, it is named after Harry Seldon from the Foundation series. which, spoiler, the book was written in the 1950s, so I think I'm allowed to spoil it at this point. It takes place in Asimov's robot universe. And what happened is the 3 laws of robotics didn't really succeed at making the galaxy evolve the way that we would want it to. And the 3 laws of robotics, a robot can't hurt a person, it has to do what a person says. These are deterministic rules, and you can't satisfy them because they're deterministic. Instead, there's a character in this book, Harry Seldon, who recognizes that the way the world evolves is a probabilistic system. And he reasons about how to change actions to make that probabilistic system evolve the way he wants with high probability. And so it seemed fitting to name this after Harry Seldon. Okay, we also define the term quasi-Seldonian, which means it's Seldonian, but you're allowed to make false assumptions, but hopefully reasonable false assumptions. So what do I mean by that? In all of our algorithms, when I say a quasi-Seldonian one so far, it means we're using Student's t-test. We're using the central limit theorem to say we assume that the sum of these 1,000 random variables is approximately normal. Okay, so what is this Seldonian framework then? The framework is a framework for designing machine learning algorithms. And it says that we should provide the user with a way of defining undesirable behavior. And then our algorithm should optimize some main objective while giving this guarantee. And a key thing is the algorithm should give this guarantee no matter how the hyperparameters are set. Performance of optimizing f could depend on your hyperparameters. But this guarantee should be subject to nothing. It must be satisfied by the algorithm always. And I'd also like to emphasize that in this talk, my goal isn't to say, look, we made a Seldonian algorithm and it's awesome. Actually, I think the algorithms that I'm going to present are really bad. They're the most simple, basic Seldonian algorithms you could create. And I'd like to argue that even they were able to get some pretty cool results. So this isn't about saying this is a great algorithm. It's about this is a cool framework, and I hope that some of the tools you guys have could create even better Seldonian algorithms. So the takeaway of this talk will hopefully be designing algorithms that match this framework is a worthy goal, not there is an algorithm out there that is good. Okay, so the algorithms that I'll give are extremely simple algorithms, and these examples are to show feasibility, so they show that you can design algorithms that have this guarantee and that are practical, and I'm promoting the framework. Okay, so let's talk about an example usage, and this one is machine learning, supervised learning, just because it's simpler to start with that. So let's say that X is a vector of features describing a person convicted of a crime, and Y is 1 if the person committed a crime in the future, and 0 otherwise. Our goal might be to find a solution theta, that's a classifier, such that y hat of x theta, that's going to be our prediction of y given input x and model parameters theta. That's a good estimator of the true label y. So one thing that we might define G to be is this definition of discrimination. So what is this? Probability y hat is 1. That's the probability that we say the person will commit a crime in the future, given that they're white, minus the probability that we say they will commit a crime in the future, given that they're not white. And then we absolute value that and subtract epsilon. So what does that do? Well, this is, by the way, called demographic parity. If we move the epsilon to the other side, remember G of theta needs to be less than 0. Moving epsilon to the other side, we get that this difference in absolute value should be small. That means these two terms should be approximately equal. So this is a way of specifying that the probability that we say you will commit a violent crime in the future, given that you're white, should be approximately the probability that we say you will commit a violent crime in the future, given that you're not white. Is that the right definition of fairness? I don't know. My goal here is not to say, here's a definition of fairness. It's to say that's one that you could use. Another that you could use is this. What is the probability that we have a false positive? That's we say that you will commit a violent crime in the future, but actually you wouldn't. So what is the probability that that will happen, given that you're white, minus the probability that that will happen, given that you're not white? That one's called predictive equality, and it's essentially saying that these two false positive rates need to be approximately equal. So that's how G could specify these fairness constraints. So what we want is our algorithm to be able to take as input the person saying minimize classification loss and use this definition of G. Are we pretty much done? No, there's probably something nagging at the back of your head. How does the user specify G? How does the user tell us this? What is our interface for defining undesirable behavior? Well, one thing we could do is say, you need to provide us with code for G. So here at C++, this is a function G that takes a solution theta as input, and it outputs the value of G for that solution. This is a horrible idea. As I learned in the RL class on Tuesday, first off, telling people to use C++ doesn't go over well. Second is, we can't do this because typically to do this, you need to know the distribution of data. right? Do I know whether a solution discriminates? That depends on the true underlying distribution of people in order to make that prediction. Let's talk about diabetes treatment. If I told you, here are 2 parameters for a controller, will this increase the amount of hypoglycemia for that person? We don't know, right? The user cannot write this function. So this is not a good way. This is not a good, it is an interface. Technically, it fits the framework. And I guess that's something to emphasize. These interfaces I'm going to talk about are example interfaces. You could come up with a totally different one as long as you're providing the user with a way to define G. This interface, terrible one. How about this? We could ask the user, and this is going to be a little better, provide me with unbiased estimates of G. So we're going to take as input theta, which is the solution, and this data set D, and we're going to output a vector now, and it's a vector of unbiased estimates of G. This is a little better because this typically doesn't require the user to know the distribution of data. They're just estimating the statistic they want to bound based on the data. So for the false positive rates, we can compute sample false positive rates and get unbiased estimates. But we can do even better than this. So if the person wanted us to bound false positive minus false positive, absolute value minus epsilon, what could we do? We could ask them to write an expression for what they want to bound. So write down an equation for G. Well, not write it, type it. And we're then going to parse it. So you write an equation for what it is you want us to bound. And this equation can use any of the common variables that are already provided. In the classification setting, this would be false positive, false positive given that you are of type 1 or type 2. In regression, this could be mean squared errors, conditional mean squared error. So what's the mean prediction error given that you are male or female? In the RL setting, this could be different expected returns. So you could provide different reward functions, and it could be the expected returns under these different reward functions. Also, the user can use other variables. If we didn't already give you a variable you want, you can write your equation in terms of a new variable as long as you also give us an unbiased estimator for that variable. And your expression can use any of the supported operators, things like plus, minus, times, divide, absolute value, min, max, etc. Okay, so if we can do that, now this person can actually express this. They're not just talking at their computer. They're writing down this equation. And our algorithm should be able to, from this, ensure that that undesirable behavior doesn't happen with high probability. Okay, so how do we go about doing this? And I guess in the spirit of not promoting an algorithm, the one I'm going to describe now in our archive paper is algorithm 11. It didn't even get a name. So our goal here is not to say, you should use this algorithm. It's to say, here's an example of how you might achieve this. So the first thing we're going to do is take our data set D and partition it into 2 sets, a candidate set and a safety set. We're going to then take the candidate set and run something that we call candidate selection, which produces one solution theta C. And this is the one solution that the algorithm is thinking about returning. We're then going to run a safety test on that theta C. So we use the held out data to test, is the algorithm confident that this solution satisfies the constraint G that the user specified? And if it is confident enough about that, then we output that solution theta C. If it's not, we say no solution found. Okay, let's dig into these 2 components a little bit more. So how does the safety test work? Consider our example before of we want the difference in false positive rates to be similar. And remember, the safety test gets as input the candidate solution and the safety data. And it's trying to output either theta C or no solution found. So the way it would work here is we would take this expression G, and actually my current code requires it to be in reverse Polish notation, so it would crash on this, but it's a simple difference. It takes the equation G and builds a parse tree from it. Right? Given that parse tree, we then bound all of the leaves. Sorry, so the leaves here correspond to either those base variables that we've already defined, or variables that the user has given us an unbiased estimator for, or something like a constant epsilon. So we bound all of the leaves, and then we propagate that bound through these different operators. We know if we have 2 ranges for confidence intervals, and I'm subtracting one from the other, we know what the resulting confidence interval is, until we get to the top, and that is then our confidence interval for G. And we check, is that strictly less than 0? If it is, then we know with high confidence this solution is meeting the safety condition. And so if it is less than 0, we return theta C. If it's not, we return no solution found. Okay, how does candidate selection work then? So we're going to pick the solution theta C. If we just pick the one that we thought was best, it wouldn't actually work very well. That's not the solution that we can guarantee is going to be best. So instead, we need to optimize our primary objective while also constraining to solutions that we think they'll pass the subsequent safety test. And so interestingly, candidate selection needs to seriously consider how the safety test mechanism is implemented, because that changes which solution is optimal. Okay, so what about in the reinforcement learning setting? In the reinforcement learning setting, our historical data D is collected from running some current policy, pi current. A solution theta corresponds to a policy or its policy parameters. And the user can then define multiple objectives, multiple different reward functions, and can require improvement or limit degradation in performance with respect to all of those reward functions. This would be one thing they could do. Here, this would mean G of theta is the expected sum of rewards given you use your current policy minus the expected sum of rewards given that you use the new policy theta that we're considering returning. What does that do? Well, when I say G of theta has to be less than 0, you get this expression, which is saying the expected performance under the current policy should be less than the expected performance under the new policy with high probability. How do we actually do this? Well, we can get estimates of both of these. So on the left side, the performance of the current policy, we can bound by just taking the Monte Carlo estimates of return. And on the right side, we can use importance sampling to get unbiased estimates of the term on the right, and we can bound both of these. Okay. So this is actually really nice because it makes it easier to specify reward functions in a sense. So consider this problem, which I think I saw first from Michael Littman in a talk, of we're trying to get from the start to the goal, and the blue cells are water, and we don't want to walk through the water. If we have a current policy for doing this, and we want to solve for a new policy that gets to the goal faster, but doesn't increase the probability of walking through the water, how do we define that reward function? It's really hard to do if we don't know the transition dynamics of the problem. But it's easy to do when we can do behavioral constraints the way we have it. We specify one of these G's to be don't walk through the water, or the amount of the number of times that it walks through the water, and it will ensure that it doesn't increase the amount of times that it walks through the water. Okay, for the sake of time, I will speed up. Oh, I do want to talk about this one. You can do an even cooler interface for reinforcement learning. So let's define a label L for each of our trajectories. And if an undesirable event occurs, that label will be 1. If an undesirable event doesn't occur, that label will be 0. So this is saying a user can look at data and say undesirable behavior occurred or undesirable behavior did not occur. That's all that they have to do in order to be able to do these labels. They don't need to know which solution causes hypoglycemia. They just need to be able to recognize what hypoglycemia is in order to specify these labels. The expected value of that label is then the probability that this undesirable event will occur. And so if we define G to be the difference in expected value of L under the policy returned by our algorithm versus the initial policy, this becomes a constraint that says, I think I wrote it out, the probability that we return a policy so that we change the policy to 1 that increases the probability of undesirable events is at most delta. And there are 2 probabilities, which makes this a little confusing. But for the sake of time, I'm going to continue on. It's saying with high probability, we won't cause undesirable behavior more often. And the key point here is the user only needs to be able to identify what constitutes undesirable events. They don't need to know what causes it to specify this. Okay, so for the sake of time, I will skip. In the case of hypoglycemia, in the case of diabetes treatment, we consider undesirable behavior to be an increase in the prevalence of hypoglycemia. And so we might say try to keep blood glucose near optimal levels. That's through F, our primary reward function, subject to the constraint that with 95% probability, the prevalence of hypoglycemia won't increase. So let's skip through this, which is just showing we can do fairness definitions and classification and go to tutoring. So in this case, we deployed a very basic tutoring system where this was a contextual bandit algorithm that was trying to decide which tutorial should I give to a user. And in this case, what this one is actually showing is that when we have very little data, the standard algorithms still return solutions, but due to the randomness in data, the solutions that they were returning aren't trustworthy, and so it was frequently violating our safety constraints. So here, horizontal axis is amount of training data, vertical axis on this plot is failure rate, how often did we violate the constraint, and in this case, the constraint was you can't hurt the performance of men or women in the classroom. The middle one is the probability we return solutions with different amounts of data, and the left is how good was our performance relative to other algorithms. This is an interesting one. This is what happened when we changed the ratio of people in the classroom to be majority men, and there was a tutorial that was better, and it was designed this way to allow for discrimination. There's a tutorial that is better for male students. And so if you deploy that tutorial and there's a majority of male students in the classroom, it increases the mean score. It increases the average score of the class. And so a standard bandit algorithm that's trying to just optimize expected score of the class will say deploy that one. But that would violate our fairness constraint that says you can't hurt the performance of one of the groups in order to increase the performance of the average. And so the standard methods tended to do this, whereas our Seldonian algorithm, the green one, this is a quasi-Seldonian algorithm, Robin Hood, never did this. It never returned the solution that violated our fairness constraint. We also applied this to, in the bandit setting, loan approval and predicting criminal recidivism and saw similar results. The key thing to note here is across all of these plots on the left, our green accuracy is comparable to that of standard methods. In the middle, we are returning solutions frequently, and we are never going above the dotted black line as the epsilon that we specified. We are not producing that undesirable behavior with high probability. And that's true across all of these different plots. Okay, the next one is type 1 diabetes treatment. So we got a detailed metabolic simulator, T1DMS, which is approved for preclinical trials in the US instead of studies on rats. So it's a good metabolic simulator. And we asked, can we improve treatment for type 1 diabetes within a simple insulin pump while guaranteeing that with high probability we're not going to increase the prevalence of hypoglycemia? On the left was the probability of undesirable behavior, the chance that we actually deployed a policy that hurt the person. Right? Blue is us. We never did it. Red is a standard policy search algorithm that just returns the policy that we think is best. And when there's very little data, it's drawing false conclusions and hurting people. Whereas our algorithm never did it. Here's the probability we returned policies. We're returning policies within 30 to 60 days, which is right where we want it for this problem. You can do this. I need to see the notes. You can do this with more subjects. So these were all 10 subjects within the simulator. You see similar results. You can do this with other definitions of safety. So this one is for mean time hypoglycemic, that other definition of safety for this problem. This one is just asking for improvement with respect to the primary objective, which is some weighted trade-off between having blood sugars that are too high or too low. You can also do this for mountain car. In this case, I'm going back to an older 2015 paper where we were only doing high confidence policy improvement, so only improve the expected return. And in this case, for mountain car, we changed it so that when the agent chooses an action, it holds that action for 20 time steps. And that is to shorten the horizon of the problem because importance sampling is high variance with respect to the horizon of the MDP. We can also do this in a sequential setting, and we did it for a 4x4 grid world, mountain car, and digital marketing. And this one I want to talk a little bit about. This was, I think, mountain car. This was one of the first experiments that I did on this. And it was really cool because I never tuned anything. I just hit the go button. And the red curves are the runs of our algorithm. And I had asked it not improve the policy, but it's not worth changing the policy until we're confident the expected return will be above -9. And in every single run, it jumps up to well above -9 before changing its policy. And NAC corresponds to, I think, NAC LSTD, or one of the natural electrocritic algorithms that's properly tuned, so it's not a safe algorithm. It has spent hundreds, thousands of episodes having its hyperparameters optimized. And this shows how much lag there is in our performance from optimal. Okay, so I'd like to finish up with some future research directions. So I pointed out that our algorithms are pretty simple. So here are just some of the obvious things that I see that could be improved. First, how do we partition data between candidate and safety? We did a 20%, 80% split. Really, this is an optimal stopping problem. You should be moving data from the safety set to the candidate set until that candidate selection mechanism says, this is the right amount of data, don't give me any more, I need to hold the rest of them to do the safety check. When we return no solution found, we don't say why. We don't say, do I not have enough data? Here's how much data you should probably give me next time, or you gave me conflicting constraints. How should we divide up that probability delta using the union bound among the different base variables that we have? It shouldn't necessarily be evenly split. And I think they're really interesting questions about how to intelligently propagate the confidence interval. In candidate selection, how do we trade off between the safety of the solution that we're thinking of returning and its primary objective value? If we focus on safety too much, we'll return terrible solutions. If we focus on the primary objective too much, we won't return solutions. So how do you properly balance this trade-off is, I think, a challenging theoretical problem. Can we make these algorithms robust to an attacker or just noisy data? Can we combine this with reward machines? Could the specification of G be given using reward machines, and can we propagate confidence intervals through them? In multi-agent RL, can we have a version of this that gives high confidence policy improvement with respect to multiple agents, or perhaps different safety constraints for each of the different agents? Can we extend some of the classification algorithms like FairLearn to be Seldonian and to topics other than classification? Of course, all improvements to off-policy evaluators are useful here. Can we get sequential algorithms? Right now, for candidate selection, we did the simple thing. We used the pseudocode from Wikipedia for CMAES. I'm sure there's something more principled that we can do there. And can we get a real human-computer interaction system for defining these behavioral constraints? And with that, I'll wrap up and just say, if you want more, there's a ICML paper from 2015 on policy improvement. We have an upcoming NeurIPS paper on these algorithms for the bandit setting, and hopefully we'll update our 2017 archive paper soon. Thanks.